Have you ever found yourself lost in deep thoughts about what nothingness truly is? Today, we are going to explore mind-blowing questions about nothingness and seek all the answers. Does nothing exist, or is there only quantum foam? Does the Schwinger effect demonstrate something from absolutely nothing? Can quantum fluctuation potentially create a universe from nothing? How does Hawking radiation convert vacuum energy into detectable matter? How did inflationary cosmology turn nothing into a universe brimming with galaxies and stars? How does the Casimir effect manipulate nothing to produce measurable forces? Can the concept of zero-point energy redefine our understanding of a true vacuum? How would vacuum decay destroy the universe? Let's delve into the answers to these questions with a comprehensive scientific perspective.
The universe is constantly expanding, but how big can it truly become? Imagine a time when all the matter in existence was squished into an incredibly tiny dot, exploding across the cosmos in what we call the Big Bang. This mind-bending event has set the stage for billions of years of cosmic growth unfolding through the invisible hand of dark energy and the dance of celestial bodies. Join us as we explore the limits of space and if everything could end in a big cosmic expansion burst. The universe is constantly expanding, a concept that has captured the attention of scientists since the early 20th century. Imagine blowing up a balloon. As you inflate it, every point on its surface moves away from every other point. This is a helpful way to visualize what happens in the universe. The space between galaxies grows, not because the galaxies themselves are moving through space, but because space itself is expanding. This expansion was first observed by astronomer Edwin Hubble, who noticed that galaxies are moving away from us and that the farther away they are, the faster they seem to be receding. This relationship suggests that the universe began from an incredibly hot and dense state around 13.8 billion years ago, a moment known as the Big Bang. This event marks the beginning of both time and space, setting everything in motion. One intriguing aspect of this expansion is that it's not just happening slowly and steadily. More recently, scientists discovered that the expansion is accelerating. This means that distant galaxies are moving away from us faster over time. To explain this unexpected behavior, scientists introduced the idea of dark energy, a mysterious force filling up the universe and driving this acceleration. Though dark energy comprises a significant portion of the universe, our understanding of it remains limited. Researchers continue to explore its implications and try to uncover the nature of both dark energy and dark matter, which together make up most of the universe's content. While scientists have made remarkable strides in understanding cosmic expansion, many questions remain, making this a vibrant field of study that continues to expand our comprehension of the universe. The discovery of the universe's expansion began in the early 20th century, reshaping our understanding of space and time. The first major clue came from the work of Edwin Hubble, an astronomer who studied distant galaxies. He observed that light from these galaxies was shifting towards the red end of the spectrum, a phenomenon known as redshift. This shift indicates that the galaxies are moving away from us. Hubble proposed that the farther a galaxy is from Earth, the faster it appears to be receding. This relationship implies that the universe itself is stretching, suggesting that it has been expanding since its origin. One key piece of evidence supporting this idea stems from the concept of the Big Bang. When scientists trace the expansion backward in time, they theorized that the universe must have started from a highly dense and hot state. To further validate this, researchers discovered what we call cosmic microwave background radiation. This faint glow, uniform across the sky, is a remnant from the early universe, confirming that it was once in a hot, dense state. Additionally, there are observations of galaxy clusters. When astronomers examine these clusters, they find that the distances between them are increasing over time. This ongoing expansion can be seen in the movement of galaxies relative to each other, supporting the idea that the universe is not static but dynamic and ever-changing. Together, Hubble's observations, the cosmic microwave background radiation, and the movement of galaxy clusters form a robust foundation for understanding the expanding universe. Each of these pieces of evidence reinforces the idea that from a singular energetic beginning, the universe has been growing and evolving into the vast cosmos we observe today. The concept of expansion is fundamental to our understanding of the universe because it provides insights into how everything we see around us has evolved over time. Imagine a balloon being inflated. The surface of the balloon represents the universe, while the dots on it symbolize galaxies. As the balloon expands, the dots move away from each other. This simple analogy helps visualize how the universe is stretching, with galaxies drifting away from one another, indicating that space itself is growing. This expansion relates directly to a pivotal moment in our cosmos known as the Big Bang. This is the event that marks the beginning of everything: space, time, matter, and energy. Recognizing that the universe has been in a continuous state of expansion since that moment allows scientists to piece together the history of the cosmos, tracing back to its origins and understanding how physical laws have shaped its development. Additionally, studying this expansion gives us clues about the fate of the universe. Depending on the effects of gravity and mysterious forces like dark energy, which fuels this expansion, we can make educated guesses about whether the universe will continue to stretch forever, eventually slow down, or even reverse course. Thus, the concept of expansion is more than a mere observation. It is a crucial key that unravels the past, present, and potential future of our universe, helping us to comprehend our place in the vastness of it. The Big Bang marks the beginning of our universe, but understanding its origins requires diving into some fascinating concepts. Scientists believe that prior to the Big Bang, the universe existed in an incredibly hot and dense state, often referred to as a singularity. Imagine a point so small that it contained all the energy and matter that would eventually give rise to everything we see today. Approximately 13.8 billion years ago, this singularity underwent a rapid and dramatic expansion. This event is what we call the Big Bang. It wasn't an explosion in space. Instead, it was an expansion of space itself. Picture blowing up a balloon, where as you inflate it, the surface stretches and expands. In a similar way, space expanded instantly, creating room for time, energy, and matter to emerge. As the universe expanded, it began to cool down. In the first few moments after the Big Bang, elementary particles like protons and neutrons formed. As cooling continued, these particles clumped together to create atoms, primarily the simplest ones like hydrogen and helium. This gradual formation laid the groundwork for stars and galaxies. The expansion of the universe didn't just lead to the creation of matter. It also set in motion the evolution of the cosmos. As galaxies spread apart, the fabric of space expanded, causing what we observe today as the universe continuing to stretch. This ongoing expansion is a fundamental characteristic that scientists still study, discovering it happens at an increasing rate, influenced by mysterious forces that govern the universe's behavior. The events believed to precede the Big Bang revolve around the transformation of an incredibly dense state into a rapidly expanding universe. This chain of events not only initiated the creation of time and space, but also set the stage for the diverse structures we see in the cosmos today. In the moments right after the Big Bang, the universe experienced an astonishingly rapid expansion known as cosmic inflation. Picture a balloon being blown up, but instead of a gentle increase, this expansion occurred at incredible speeds, far surpassing the speed of light. It happened within a fraction of a second, expanding from something incredibly tiny to a size much larger than our observable universe today. The concept of inflation helps explain several observations about the universe. One key piece of evidence is the uniformity of the cosmic microwave background radiation. This radiation fills the universe and serves as a faint afterglow of the heat from the Big Bang. Scientists have found that this radiation is remarkably smooth and uniform in all directions, suggesting that regions of space were once in close contact, allowing for even temperature distribution. Cosmic inflation accounts for this, as the rapid expansion would have stretched out any initial irregularities. Another compelling piece of evidence comes from the large-scale structure of the universe. The way galaxies are distributed today follows a pattern that supports the idea of inflation. These structures originated from tiny quantum fluctuations in the early universe, which were then exaggerated by inflationary expansion, leading to the galaxies and clusters we see now. Lastly, the observed rate of expansion of the universe today, known as the Hubble constant, also hints at this rapid early growth. By looking closely at the redshift of distant galaxies, astronomers can see how fast these galaxies are moving away from us, indicating how expansion continues on from the early moments after the Big Bang. Together, these observations create a compelling case for the idea that the universe expanded at astonishing speeds in its earliest moments, shaping everything we know about it today. However, within the balloon are unseen structures holding everything together, much like dark matter does for our universe. While ordinary matter, such as stars and planets, only makes up a small part of the universe, dark matter is believed to constitute a significant portion. It doesn't emit light or energy, making it difficult to detect directly. Yet scientists know it exists because of the gravitational effects it exerts on visible matter. For instance, galaxies spin at speeds that wouldn't keep them together if only the visible matter was present. Dark matter provides the necessary extra mass to hold galaxies intact and ensures they don't fly apart. This presence of dark matter affects how the universe expands. The expansion is influenced by the combined gravitational pull of all the matter, both visible and dark. If dark matter were absent, galaxies would drift apart much faster than they currently do. Instead, the gravitational pull from dark matter acts like a stabilizing force, slowing the pace of expansion, especially at large scales. Furthermore, understanding dark matter helps scientists grasp the universe's fate. Current measurements suggest that, while the universe is expanding, the rate of this expansion is accelerating. This acceleration is linked to dark energy, a mysterious force thought to be different from dark matter. Together, both dark matter and dark energy shape how structures form, evolve, and interact over cosmic time. Dark matter has profound implications for the universe's geometry, structure, and expansion rate. By influencing how galaxies cluster and behave, it plays a pivotal role in the cosmic story, profoundly impacting the future trajectory of the universe and our understanding of its ultimate destiny. The Big Crunch hypothesis presents a scenario for the ultimate fate of the universe, suggesting that the cosmos could eventually stop expanding and begin to contract. Imagine the universe as a balloon filled with air, where each section is moving away from the others as the balloon inflates. Currently, observations show that galaxies are drifting further apart, indicating that the universe is expanding. However, if the total amount of matter and energy in the universe is significant enough, this gravitational pull might dominate over the expansion. If that occurs, at some point, the expansion could slow down, halt, and revise. Picture the balloon starting to deflate as it loses air. The material gathers tighter and tighter, leading to a collapsing state. As the universe contracts, galaxies would draw closer together, and enormous gravitational forces may lead to dramatic changes. Stars might begin to collide, and the cosmic structures we know could destroy each other in this new chaotic environment. Eventually, all the matter in the universe could converge into a singular point where the laws of physics, as we understand them, may no longer apply, mirroring the conditions that theorists believe occurred at the beginning of time, the Big Bang. The Big Crunch envisions a cyclical universe, where expansion is followed by contraction, leading to a final state that is starkly different from the vast, spreading cosmos we see today. It raises fascinating questions about the nature of the universe, and whether this process might happen only once or repeat in a series of cosmic cycles. The Big Crunch is a theoretical scenario about the future of the universe, where everything could eventually collapse back into a singularity. For this dramatic ending to occur, several specific conditions must be met regarding the universe's density and expansion. First, the overall density of the universe must be higher than a critical threshold. This density is a measure of the amount of matter and energy in space. Imagine the universe as an expanding balloon. If there is enough mass, the gravitational pull would be strong enough to stop the expansion and start pulling everything back together. This would require a certain amount of ordinary matter, and dark energy, which collectively influence the universe's fate. Next, the rate of expansion of the universe must slow down. Currently, the universe is expanding, and observations suggest that this expansion is actually speeding up due to dark energy. For a Big Crunch to unfold, this trend would need to revise. Gravity would have to regain control over the expansion, resulting in a gradual slowing until it halts and then changes direction. Also, dark energy plays a crucial role in this process. If dark energy were to weaken or disappear entirely, the universe might be able to collapse. In this scenario, the attractive force of gravity would dominate, pulling galaxies, stars, and eventually all matter back toward a central point. For the big crunch to happen, there must be sufficient matter to halt the universe's expansion, a reversal of the current accelerating expansion, and a change in the behavior of dark energy, leading to a point where gravity eventually reigns supreme, causing everything to draw inwards. This fascinating possibility is just one of several theories about the ultimate fate of the cosmos. The Big Crunch is one potential scenario for how our universe might end. To understand it, let's first consider the universe's expansion. After the Big Bang, everything in the universe began spreading apart, like dots on a balloon as it's inflated. In the Big Crunch theory, this expansion doesn't last forever. Instead, imagine that the balloon starts to lose air and slowly begins to contract. Gravity pulls everything back together, and over an immense period, galaxies would merge, stars would collide, and galaxies would eventually squeeze into a singular point once more. This idea contrasts with other end-of-universe scenarios. One such scenario is the Big Freeze, where the universe continues to expand forever. In this case, galaxies drift farther apart, stars burn out, and the universe gradually cools down over billions upon billions of years. It reaches a state where no light or heat remains, resulting in a dark and cold cosmos. Another possibility is the Big Rip. In this scenario, the universe expands at an accelerating rate, driven by mysterious energy known as dark energy. As this expansion grows stronger, it could eventually tear apart galaxies, stars, and even atomic structures themselves, leading to a dramatic and violent end. The Big Crunch presents a cyclical view of the universe, where expansion is followed by contraction, potentially leading to another Big Bang and the start of a new cycle. In contrast, the Big Freeze depicts a universe that endlessly cools, while the Big Rip suggests a catastrophic ending driven by an uncontainable force. Each theory presents unique implications about the fate of everything we know, leading scientists to explore and debate these intriguing possibilities about the universe's ever-unfolding story. The heat-death theory is a fascinating idea about the long-term future of the universe. Imagine the universe as a gigantic, ever-expanding balloon. As this balloon gets bigger, the gases inside spread out and the temperature drops. In a similar way, as the universe expands, everything within it, stars, galaxies, and even the very fabric of space itself, continues to move further apart. According to this theory, over an incredibly long time, the universe will reach a point where it can no longer sustain processes that require energy. Stars will exhaust their nuclear fuel, leading them to dim and fade away. Once all the stars have died, the universe will be filled with dark, cold matter, and the remaining energy will be too spread out to do anything useful. This scenario leads to a state of maximum entropy, where energy is so evenly distributed that there are no gradients to drive any physical processes. It's like a kitchen filled with a perfectly mixed bowl of ingredients. No matter how you try, you cannot create heat or energy from something that is uniformly mixed. In this stark and silent universe, even black holes will eventually evaporate over immense time frames. With no light, no stars, and no structure remaining, the universe will exist in a state of complete equilibrium, where nothing much happens at all. This heat death signifies a universe that is cold, dark, and lifeless, a quiet, desolate end to the extraordinary journey of cosmic evolution. The heat death scenario emerges from the idea that the universe is expanding, potentially for eternity. As the universe expands, galaxies drift further apart. Imagine blowing up a balloon. As you inflate it, the dots on its surface move further from each other. In the vastness of space, this means stars will eventually exhaust their fuel and burn out, leading to a gradual dimming of the cosmos. In this scenario, as stars die and matter spreads thinly across an ever-growing universe, temperatures would cool. Eventually, even the remnants of stars will fade away, leaving behind only cold and dark remnants, like black holes and subatomic particles. Essentially, it describes a state where the universe reaches maximum entropy, resulting in a uniform temperature and no usable energy to sustain processes or life. Imagine a room filled with an equal distribution of air. No areas are noticeably colder or warmer, leading to stagnation. To assess scenarios like heat death, researchers analyze the universe's expansion by studying galaxies and how they are moving away from each other. Scientists gather insights into the universe's fate. For instance, if the expansion continues to accelerate indefinitely, heat death becomes more plausible as energy becomes increasingly diluted. However, there are competing theories. The concept of the Big Crunch suggests that the universe might eventually stop expanding and start collapsing in on itself, leading to a highly energetic state before a potential rebirth. Alternatively, scenarios like the Big Rip propose that the universe might expand so rapidly that it tears apart matter itself, resulting in a violent end. Each scenario is evaluated through advanced mathematics and physics, allowing scientists to calculate probabilities based on current data. They consider various factors such as the amount of dark energy and dark matter, both of which play significant roles in the universe's expansion and shape its destiny. By combining empirical observations with theoretical frameworks, scientists develop a clearer picture of how likely each scenario is, continuously refining their understanding as new discoveries emerge. The Big Freeze scenario presents a chilling perspective on the future of our universe. As the universe continues to expand, galaxies will gradually move farther apart, creating vast stretches of emptiness. Picture a balloon slowly being inflated. As it grows, the dots on its surface move away from each other. In the distant future, stars will burn out, and galaxies will drift into oblivion, leaving a dark, cold expanse. In this scenario, the energy in the universe becomes increasingly diluted. Instead of being filled with vibrant stars and lively galaxies, it will mostly consist of a sparse scattering of particles, predominantly hydrogen and helium, along with a little bit of dark matter. Over an incredibly long span, stars will cease to form, leading to a decline in cosmic activity. Eventually, even the remnants of once bright stars will fade, leaving behind only cold, blackened remnants. As time passes, temperatures will drop, and the universe will edge closer to absolute zero, the point at which molecular motion nearly stops. While this may sound like a desolate ending, it's essential to understand that this transformation will unfold over trillions of years, far beyond our current understanding of time. The Big Freeze suggests that, while the universe expands endlessly, it will gradually become a dark and quiet place, a stark contrast to the dynamic cosmos we witness today. The Big Freeze and heat death are concepts that both relate to the fate of the universe, but they describe different aspects of the end scenario. Let's start with the Big Freeze. Imagine the universe expanding like a balloon. As it stretches, galaxies move farther apart. Over an incredibly long time, this expansion continues, leading to a situation where stars gradually burn out and galaxies drift away from each other so much that they become isolated. This is the Big Freeze, a cold and dark universe where the remnants of stars and galaxies fade into silence. Everything will be so far apart that interactions will become rare, and it feels like time has slowed down drastically. On the other hand, heat death refers specifically to the state of maximum entropy in the universe. Entropy is a measure of disorder, and as the universe expands, energy becomes more evenly spread out. Over an immense timeline, all processes will reach a state where no energy is available to do work. Think of it like a car running out of gas. Eventually, it will just sit there, unable to move. In this scenario, every star will have exhausted its fuel, and all sources of energy will be depleted, leaving a lifeless and unchanging cosmos. So, while both concepts overlap in the lead-up to the end of the universe, the Big Freeze focuses on the cold and dark isolation that results from the expansion, while heat death emphasizes a state of complete uniformity and inactivity. Ultimately, the two are interconnected parts of a long cosmic timeline that envisions a universe where activity and energy dissolve into stillness. The Big Freeze scenario, often discussed in relation to the ultimate fate of the universe, is characterized by continual expansion that leads to a gradual cooling and diminishing of energy throughout space. Several key observables can indicate that this scenario is unfolding. One of the most prominent signs is the measurement of the universe's expansion rate. Scientists have observed that galaxies are moving away from each other, and this trend has been accelerating over time. This acceleration is believed to be driven by a mysterious force they call dark energy. If this trend continues unabated, It suggests that the universe is heading towards a future where galaxies drift farther apart, effectively isolating them over immense distances. Another observable link to the Big Freeze is the cosmic microwave background radiation, a faint afterglow from the early universe. Analyzing this radiation provides insights into the universe's temperature. As the universe expands and ages, the heat from this radiation becomes diluted, resulting in lower temperatures. If ongoing observations show a steady decline in temperature over time, it would align with predictions of the Big Freeze. Additionally, the density of matter in the universe plays a crucial role. If future measurements reveal that the density remains below a certain critical threshold, it would indicate that gravitational forces will not be sufficient to halt the expansion. Instead, it would likely continue indefinitely, contributing to the Big Freeze scenario. Furthermore, examining the behavior of distant supernovae can offer crucial evidence. These bright explosions serve as beacons to measure distances in the universe. If their brightness continues to suggest a uniform acceleration in the expansion of the cosmos, that would reinforce the idea of an unattainable future where galaxies are no longer able to cluster together. Together, these observables provide a compelling picture of a universe that could be spiraling into an infinite state of coldness and isolation, devoid of interactions among celestial bodies over a vast timescale. The Big Rip theory presents a dramatic scenario for the future of our universe. It builds on the observation that the universe is expanding at an accelerating rate. Imagine the universe as a balloon that keeps inflating faster and faster. As this happens, if the force driving this acceleration, the mysterious dark energy, grows stronger over time, the consequences for everything in the universe could be catastrophic. In this scenario, galaxies would start to drift away from each other at an ever-increasing speed. The gravitational bonds holding galaxies together would weaken to the point of breaking. Eventually, the gravitational pull holding together clusters of galaxies would also falter, leading to their dissolution. This relentless expansion wouldn't stop there. Even the atoms within the stars could be torn apart. The forces pulling everything apart would become so strong that they would overcome all attractive forces in the universe. As the universe nears this endpoint, the fabric of space itself would seem to unravel. Star systems would face their doom, planets would be stripped from their orbits, and ultimately, everything that exists could be violently torn apart in a grand finale. This end, predicted by the Big Rip theory, emphasizes not just separation at great distances, but a fundamental alteration of matter itself, resulting in a universe where everything is reduced to individual particles or even smaller components. The cyclic or oscillating universe theory presents a fascinating idea about the life of the cosmos. Instead of viewing the universe as having a single beginning with the Big Bang, this theory suggests that our universe undergoes endless cycles of expansion and contraction. To understand this, imagine a balloon being inflated. As the balloon grows larger, it stretches out. When you let the air out, it shrinks back down. This is similar to the universe expanding and then collapsing back on itself. According to this theory, after a period of expansion, the gravitational pull of matter would eventually cause the universe to slow down and then reverse its growth. This contraction phase would lead back to a highly dense state, comparable to the conditions just before the Big Bang. At this critical moment, the theory posits that a new expansion occurs, leading to the birth of a new universe, repeating the cycle. One key aspect of this idea is that it allows for the possibility of the universe being eternal, with no definitive beginning or end. The transitions between expansion and contraction might create a universe where new generations of stars and galaxies emerge, allowing different states of existence to unfold over time. The universe, as a constantly stretching fabric, where the largest events, like galaxies moving away from each other, are only half the story. When we zoom in to examine the fundamental particles, such as electrons and quarks, we encounter a strange and bustling world. Quantum theory tells us that these particles do not exist in fixed positions. Rather, they exist in probabilities, acting both like waves and particles. This peculiar duality implies that, at any moment, there is a chance to find these particles in various states and locations. Moreover, the energy fluctuations present in this quantum realm play a significant role in the overall expansion. Even in what is considered empty space, known as a vacuum, there are fluctuations of energy that create virtual particles. This energetic backdrop could influence the rate at which space itself expands, merging the effects of quantum mechanics with cosmic evolution. When we consider the entire cosmos, applying the principles of quantum theory can help explain not only how the universe grew after the Big Bang, but also why its expansion seems to be accelerating today. Such acceleration hints at mysterious forces, often referred to as dark energy, which could intertwine with the principles of quantum fluctuations. Quantum theory provides a unique perspective, suggesting that the universe is not merely expanding silently, but is a dynamic arena where the smallest scales of reality interact continuously. This interaction not only shapes our experiences, but may redefine our understanding of time, energy, and the very fabric of existence itself. In the early universe, shortly after the Big Bang, everything was incredibly hot and dense. This dense environment was filled with energy, and within that energy, tiny fluctuations were constantly occurring. These fluctuations, known as quantum fluctuations, can be thought of as brief appearances and disappearances of energy in a vacuum. They are essentially the universe's way of showing some unpredictability at a very small scale. Now, imagine these fluctuations like tiny bubbles in a boiling pot of water. Each bubble forms, grows, and then disappears. But in the early universe, these fluctuations were not just fleeting occurrences. Instead, they could have had significant implications for the overall expansion of the universe. When these tiny bubbles of energy became larger, they could have created small regions of varying energy density. As the universe began to expand, some of these varied regions influenced how quickly different parts of the universe expanded. Areas with slightly more energy than their surroundings could push outward more forcefully, causing those regions to stretch and grow faster than others. This effect contributed to what we see today, which is an uneven distribution of galaxies and cosmic structures. Furthermore, the rapid expansion of the universe during a period known as inflation could have been triggered by these fluctuations, leading to a brief but intense growth phase. During inflation, the universe expanded at an astonishing rate, which smoothed out much of the initial irregularities, but also set the stage for the large-scale structures we observe now. Quantum fluctuations played a fundamental role in shaping the early universe's expansion by introducing variations that would influence the movement of matter and energy. These tiny ripples in the fabric of space and time set the groundwork for the complex universe we experience today. Gravitational waves are ripples in space and time, created by incredibly energetic events, like the collision of two black holes or neutron stars. When these cosmic events happen, they send waves through the universe that can be detected on Earth, allowing scientists to gather valuable information. By studying these waves, researchers can learn about the properties of the objects that produce them, such as their mass and distance. This information is crucial for understanding the expansion of the universe because it helps us measure how fast the universe is stretching over time. As gravitational waves come from very distant events, they also provide a kind of cosmic perspective that light alone cannot offer. For example, light from distant galaxies can be affected by the expansion of space, which may obscure or alter its path. However, gravitational waves travel unobstructed, allowing scientists to measure the universe's expansion directly and accurately. Furthermore, when gravitational waves are associated with events like supernovae or from the merging of neutron stars, they can serve as standard candles to better determine distances. This helps create a clearer picture of how fast the universe is expanding now compared to how it was in the past. By piecing together these observations, scientists can map out the history of cosmic expansion, revealing the universe's journey through time and providing insights into its ultimate fate. Gravitational wave astronomy has opened up an exciting new chapter in our understanding of cosmic expansion. Traditionally, astronomers relied on light from distant objects to measure how fast the universe is growing. However, gravitational waves offer a different perspective. By detecting ripples in space and time caused by massive events, like two black holes merging, one of the significant discoveries came from observing gravitational waves associated with the merger of neutron stars. When these stars collide, they not only produce gravitational waves but also release light in various forms, including gamma rays. By observing both the gravitational waves and the light that followed, scientists were able to calculate the distance to the event with great precision. This distance measurement, combined with the speed of the light we see, allowed researchers to refine the rate of cosmic expansion, known as the Hubble constant. This approach directly ties cosmic events to distance measurements in a more accurate way. The excitement lies in the potential discrepancies with previous measurements, based solely on light signals from supernovae or other celestial objects. When gravitational waves are involved, it's like having a two-way communication, one through the invisible waves and another through visible light. The ongoing research into gravitational waves promises to deepen our understanding of the universe's expansion, allowing us to better grasp how quickly different parts of the universe are moving away from each other. This fusion of gravitational wave data with traditional astronomical tools is gradually reshaping our cosmic map, leading to more accurate models of the universe's history and its future. As this field evolves, we may soon uncover answers to fundamental questions about the nature of dark energy, the mysterious force thought to be driving the accelerated expansion of the universe. Discoveries in cosmic growth shed light on the powerful forces that shape our universe. These findings reveal the fundamental interactions between matter, energy, and gravity on a vast scale. Imagine the universe as a balloon expanding. As it inflates, galaxies and clusters move away from each other, helping us understand the effects of dark energy, the mysterious force driving this accelerated expansion. By studying the distribution of galaxies and the cosmic microwave background radiation, we can map out how matter clumps together under the influence of gravity. This process, known as gravitational attraction, pulls matter into the dense regions that later become galaxies. Understanding this clumping behavior provides insights into the evolution of structure within the universe. Moreover, these findings assist in uncovering the role of dark matter, which is unseen yet essential. While we cannot see dark matter directly, its presence is felt through its gravitational influence on visible matter. Through various observations, scientists can infer how dark matter affects galaxy formation and clustering, revealing a web-like structure underlying the universe's expansion. Each discovery helps us piece together the cosmic puzzle. It enhances our understanding of how forces like gravity, dark energy, and dark matter interact and influence the universe's growth, painting a clearer picture of our cosmic environment and how it came to be. The distribution of galaxies and the influence of gravity over billions of years. This allows researchers to visualize how the universe might evolve, including whether it will continue to expand indefinitely, eventually stop, or even revise. Technological advancements are not just helpful tools, they reshape our theoretical landscape. As we continue to innovate, we unlock deeper mysteries of the cosmos, enriching our understanding of how the universe is expanding and what that means for its ultimate fate. Several upcoming missions and research projects are poised to enhance our understanding of cosmic expansion. One such initiative is the European Space Agency's Euclid satellite, which is designed to map the distribution of dark energy and dark matter across the universe. By examining how galaxies are distributed and how they move apart, scientists hope to uncover crucial details about the forces driving the universe's expansion. Another significant project is NASA's James Webb Space Telescope, set to observe the oldest light from the universe. Webb will provide insights into the formation of galaxies and the early cosmos. By studying distant galaxies, researchers can determine how the expansion has changed over time, leading to a better understanding of the universe's evolution. In addition, ground-based observatories like the Vera C. Rubin Observatory in Chile are preparing to contribute valuable data. This facility will conduct regular surveys of the night sky, documenting how galaxies drift apart over time. Such comprehensive observations are vital for detecting the subtle changes in cosmic expansion. Moreover, various collaborations and experiments aim to refine measurements of key cosmic indicators, such as supernovae and gravitational waves. Tracking these phenomena helps scientists establish a clearer timeline of the universe's growth and acceleration. Each of these missions and projects collectively enhances our ability to peer deeper into the cosmos, providing insights that could reshape our understanding of cosmic expansion and the fundamental forces at play in the universe. Studying the expansion of the universe presents several intriguing challenges for astronomers and scientists. One of the primary difficulties lies in measuring vast distances. Since the universe is incredibly large, standard measurements are often inadequate. To overcome this, scientists use reference points such as galaxies to determine distance. However, Accurately identifying and calibrating these references requires sophisticated techniques, which can introduce uncertainties. Another challenge is understanding the light emitted by distant objects. As galaxies move away from us due to expansion, their light shifts toward the red end of the spectrum, a phenomenon known as redshift. This shift can vary greatly, complicating how we interpret the data. Observing these distant galaxies requires highly sensitive instruments, and even slight errors can lead to significant miscalculations. In addition, cosmic background radiation, the afterglow of the Big Bang, provides clues about the early universe. Yet, its detection is not straightforward. This ancient radiation is faint and must be separated from other sources of interference, like light pollution from our own galaxy. Moreover, the universe is influenced by various components such as dark matter and dark energy, which are not directly observable. Understanding their roles in expansion involves complex theoretical models, adding another layer of uncertainty to our observations. As scientists continue to grapple with these challenges, they develop new technologies and methods to enhance our understanding of the universe's expansion. Piecing together this vast cosmic puzzle, astronomers face challenges when measuring the expansion of the universe. To ensure accuracy, they take several careful steps to address potential biases and limitations in their data. One major approach is utilizing multiple methods of measuring distance and expansion rates. By comparing results from different techniques, like observing supernovae, clusters of galaxies, and cosmic microwave background radiation, astronomers can cross-check their findings against one another. This triangulation helps identify and correct inconsistencies that might arise from a single method. Another critical factor is the selection of the objects being studied. Astronomers strive to choose a wide range of celestial bodies and ensure that they represent various types of galaxies and environments. This diversity helps prevent selection bias, where certain types of events or formations might skew the measurements if used exclusively. Additionally, astronomers pay careful attention to the instruments and technology used for these observations. Enhancements in telescope design and data analysis techniques have allowed them to gather more precise measurements over time. They also account for systematic errors, known factors that could influence results, such as how light behaves differently when passing through various cosmic materials. By understanding and correcting for these influences, they work to ensure that their findings are as accurate as possible. Finally, transparency in data and methodologies is essential. Astronomers share their findings and invite peer review to encourage scrutiny and validation from the scientific community. This collaborative approach helps ensure that any potential biases are caught and addressed before conclusions about the universe's expansion are drawn. Through these combined efforts, astronomers strive for a clearer and more accurate understanding of how the universe is growing. Current models of the universe's expansion are fascinating, but they are not without their puzzles. One major anomaly is the observation of the universe's accelerating expansion. Scientists expected a gradual slowdown of expansion due to gravity pulling galaxies together, but data reveal that this expansion is actually speeding up. This surprising behavior suggests a force acting against gravity, which we call dark energy. Yet, dark energy itself remains a mystery, with no one fully understanding what it is or how it works. Another intriguing twist comes from the Hubble constant, which measures the rate of expansion. Different methods of measuring this rate produce conflicting results. Observations of the oldest light in our universe, produced shortly after the Big Bang, suggest a slower expansion compared to direct measurements of distant galaxies today. This inconsistency raises questions about our understanding of the universe's history and its expansion rate. Additionally, we've encountered the cosmic microwave background radiation, which is the afterglow of the Big Bang. This radiation provides crucial information about the early universe's state, yet some anomalies in its temperature fluctuations suggest that the universe isn't as uniform as we thought it to be. These irregularities challenge certain assumptions about cosmic inflation, the rapid expansion shortly after the Big Bang that is believed to have set the stage for our observable universe. Finally, there are the large-scale structures in the universe, like galaxy clusters. Their distribution does not fit neatly with existing models, indicating that we may be missing essential elements in our understanding of cosmic evolution. Each of these anomalies highlights gaps in our knowledge and points to the potential need for new theories or revisions of current models to better explain the mysteries of our universe. speculative physics and futuristic theories have become essential components in our quest to understand the ever-expanding universe. At its core, cosmic expansion describes how galaxies move away from each other over time, a phenomenon first observed in the early 20th century. However, as scientists delve deeper, new ideas emerge, adding complexity to this initial picture. One significant concept is dark energy. This mysterious force seems to drive the acceleration of cosmic expansion. Imagine it as a hidden wind pushing galaxies apart, becoming more influential as the universe stretches. Speculative physics seeks to explain the nature of dark energy, considering whether it could be a constant force, if it's tied to the fabric of space itself, or if it might change over time. Another layer comes from theories like string theory and quantum gravity. These frameworks suggest that fundamental particles and forces might be interconnected in ways we have yet to fully comprehend. They propose that the cosmos could be made of tiny vibrating strings or higher dimensional spaces. Such ideas could eventually shed light on how expansion relates to the fundamental structure of the universe. Then there's the exploration of parallel universes or multiverse. This exciting theory suggests that our universe might be just one of many, possibly expanding at different rates or even governed by different physical laws. If multiple universes exist, understanding their expansion could unlock insights into our own universe's behavior. Moreover, concepts such as inflation introduce a dramatic period of rapid expansion just after the Big Bang. This moment set the stage for the universe we see today. Investigating this period raises questions about how it relates to dark energy and current expansion. All these speculative ideas provide possibilities rather than definitive answers. They challenge scientists to think outside established frameworks, sparking new research and discoveries. As we engage with these theories, our understanding of cosmic expansion becomes more intricate and profound, reflecting the complexity and wonder of the universe itself. In the realm of fiction, many works have creatively explored the concept of the universe's expansion, often taking inspiration from real scientific theories, while also bending the rules of reality to ignite imagination. One notable example is the science fiction series The Expanse. This story presents a universe where humanity has colonized the solar system, alluding to the vastness of space and the gaps between worlds as an essential aspect for exploration and conflict. While it captures the essence of humanity's urge for discovery, it reflects a more immediate and navigable expanse rather than the large-scale expansion scientists describe. Scientists are generally very open to reconsidering current ideas about the expansion of the universe when presented with new evidence or theories. The scientific method thrives on questioning established concepts and being willing to adapt our understanding based on new observations. For many years, the idea that the universe is expanding has been widely accepted, especially after the discovery of galaxies moving away from us. However, as technological advancements lead to new types of measurements, including the observation of distant supernovae or the variations in cosmic microwave background radiation, scientists can gain fresh insights. If new theories emerge, like speculative ideas surrounding dark energy or modifications to gravity, scientists will rigorously test them against existing data. A theory that offers a better explanation or helps resolve current inconsistencies will attract serious attention. Revising ideas is not a sign of weakness, but rather a hallmark of a robust scientific field. It reflects the community's commitment to truth and understanding. Prominent researchers often engage with newer theories openly, leading to discussions in journals, conferences, or public forums. Such interactions foster an environment where knowledge evolves, allowing science to build on its past while continually seeking a clearer picture of the cosmos. The concept of an expanding universe has significantly impacted both philosophy and religion by challenging our understanding of existence and our place in the cosmos. Traditionally, many cultures viewed the universe as static and eternal, often paralleling their beliefs about creation and existence. However, the revelation that the universe is continuously stretching, growing ever larger since the Big Bang, reshapes these foundational perspectives. Philosophically, the notion of an expanding universe opens up questions about infinity, time, and change. If the universe is expanding, it suggests that everything is in constant motion and transformation. This idea leads thinkers to explore what it means to exist in a continually changing reality. It invites discussions about the nature of creation. Does the universe have a beginning? And if so, What occurred before that moment? Such inquiries challenge our previous understandings of cause and effect, pushing the boundaries of human thought. From a religious standpoint, the expanding universe can lead to a reassessment of creation narratives found in sacred texts. Some religious interpretations may struggle with the scientific view, as ancient texts often describe a fixed universe created once and for all. In contrast, the expanding cosmos suggests a more dynamic view of creation, which may resonate with some spiritual perspectives that see the divine as continuously active in the unfolding of reality. Moreover, this idea can provide a sense of connection to a greater whole. As people learn that we are part of an expansive universe, it can inspire feelings of solidarity with others and the universe itself. Many find comfort in the idea that humanity shares a collective journey through this vast, forever-changing space. Overall, the discovery of an expanding universe has opened a pathway for new interpretations and dialogue between science, philosophy, and religion, encouraging an ongoing exploration of what it means to exist in such a vast and mysterious cosmos. The concept of our universe being either infinite or finite carries significant socio-cultural implications that touch upon how we view our place in the cosmos. If we consider an infinite universe, it suggests that space and time stretch endlessly, without bounds. This might instill a sense of wonder and humility within us. The idea that the possibilities of existence and experiences are limitless can inspire creativity, curiosity, and exploration. It invites philosophical questions about the nature of reality, existence, and our interconnectedness with all living things, encouraging collaboration and a shared quest for understanding. On the other hand, a finite universe implies that there is a defined limit to what exists. This can lead to a sense of urgency in how we treat our planet and resources, knowing there may be an end to everything we know. Such a perspective can promote stewardship of the earth, as we might feel a responsibility to preserve it for future generations. Societally, it may provoke deeper reflections on mortality, purpose, and the legacy we leave behind. Communities might become more close-knit, as the finite nature of existence fosters a greater appreciation for the time and experiences we share. Additionally, the discourse around whether the universe is finite or infinite can fuel various belief systems and spiritual ideologies. Different cultures may interpret these ideas through their religious or philosophical lenses, leading to diverse narratives about creation, existence, and the meaning of life. How we understand the universe profoundly shapes our societal values, relationships, and aspirations, highlighting the intricate bond between science and the human experience. Cultures around the world have diverse interpretations of the universe, especially concerning its expansion and ultimate fate. For many, the cosmos is not just a physical space, but deeply intertwined with cultural beliefs, mythology, and philosophical ideas. In ancient cultures, the universe was often viewed as a static entity, where the heavens were unchanging. For example, in various indigenous traditions, the sky was seen as a dome with stars and celestial bodies placed by creators or divine beings. This perspective emphasizes harmony and balance, suggesting that the universe remains in a fixed state as a reflection of earthly life. As scientific understanding advanced, particularly in the last century, many cultures began to embrace new interpretations of cosmic expansion. The idea that the universe is continuously stretching was popularized by astronomers who observed the redshift of distant galaxies, indicating they are moving away from us. In Western scientific discourse, this led to the Big Bang Theory, explaining the universe's beginning and suggesting an ongoing evolution that might eventually lead to scenarios like a big freeze or a big crunch. Eastern philosophies, however, offer a different lens. In Hindu cosmology, the universe is viewed cyclically, where creation and destruction happen in repeated cycles rather than a straight line towards an end. This perspective welcomes the notion of cosmic expansion, while also incorporating a belief in eventual dissolution. African cosmologists often hold an interconnected view of the universe, where expansion may symbolize growth and change within the community and environment rather than fear of an unknown end. This interconnectedness reflects a deep understanding of one's place in the cosmos, suggesting that humanity and the universe evolve together. In contemporary discussions, many cultures are expressing more curiosity about cosmic science, often infusing modern understandings with traditional beliefs. As they contemplate the universe's fate, questions about existence, purpose, and the potential for life beyond Earth blends scientific inquiry with spiritual and existential reflection. This encourages a richer dialogue on how humanity fits into a universe that is ever-expanding and dynamic, no longer seen as a distant and separate reality, but as part of a larger narrative that includes our stories, cultures, and the symbols we create. Mathematics plays a crucial role in understanding the expansion of the universe, acting as the backbone of many scientific theories. To grasp this concept, envision mathematics as the toolkit that scientists use to describe how celestial objects move and interact. One foundational theory is the Big Bang theory, which posits that the universe began from a tiny, hot, and dense state and has been expanding ever since. To observe this expansion, scientists measure how far galaxies are from us and how fast they appear to be moving away. This is where mathematical formulas come into play. They help researchers quantify relationships, such as how the speed of a galaxy's movement is linked to its distance from Earth. This relationship suggests that the universe is expanding uniformly, much like dots on an inflating balloon move away from each other as it grows. Additionally, advanced mathematics allows scientists to create models of spacetime, a concept that merges three dimensions of space with time into a single framework. These models help illustrate how gravity affects the fabric of the universe, influencing the rate of its expansion. For instance, Einstein's theories incorporate complex equations to predict how mass and energy will curve spacetime and subsequently influence the universe's expansion rate. Mathematical tools, including calculus and statistics, enable scientists to analyze data collected from telescopes and other instruments. By interpreting this data mathematically, researchers can draw conclusions about the universe's past, present, and future. Through these calculations, they can suggest concepts such as dark energy, a force believed to be accelerating the expansion, which further demonstrates how mathematics connects observations with theoretical predictions about the universe's behavior. Mathematics is not just numbers and equations. It is a language that allows us to articulate the wonders of the cosmos, helping us decode the ever-expanding universe around us.